All right, so the exceptions to the electron configuration, okay? Before we talk about the exceptions, I need to tell you when electrons have, or atoms have the most stability. They are if they have a full outer shell of 8 electrons. We call that an octet. And then when we're talking about the octet, we're talking about in the outermost s and p. Okay, the outermost s and p orbitals. So these are going to be in the s2p6 when that is full. Okay, what group on the periodic table fills up s2 and p6? Noble gases. Yes, that's correct. Who said that? Good job over there in that corner. Okay, no. So when you have a full octet, those are called our valence electrons, or our outermost electrons. So when I say outermost, when I'm talking about neon, I would be talking about in the 2s2, 2p6. If I was talking about argon, it would be 3s2, 3p6. Okay, that's when it's the most stable, which, by the way, is why the noble gases don't participate in reactions, because they have a full octet, so they're happy little campers and they won't react. Okay, if a sublevel is full, okay, for instance, if my D sublevel is completely full, it's more stable than a partially filled. Okay, if my S sublevel is filled with 2, it's more stable than a partially filled. Okay, and then the next best thing to full is being half full. Okay, and so that would be like if my D orbital had 5, my P had 3, or my F had 7. In other words, I have 1 electron going up in each of the orbitals. So that makes them more stable. So in order to achieve greater stability, there are some elements that will deviate from the standard filling that we've been doing. Okay, there are some in the F block that do it as well, but we're not going to worry about those. Okay, we're going to worry about these: chromium, molybdenum, or as you learn to spell it, molybdenum, but it's actually pronounced molybdenum, copper, silver, and gold. Okay, so if you look at the periodic table over here on the wall, copper and silver and gold are all in the same group. Okay, and so are chromium and molybdenum. Tungsten is also in that same group, and it does follow that deviation, but we don't deal with tungsten hardly at all, and so we're not going to worry about it. It's not one you have to memorize. But these 5 you do just have to memorize. Okay, so we're going to do an example with chromium and an example with silver. Okay, so when we're doing chromium, we would expect chromium, what we expect is for it to be what? The way that I taught you last week would be, first of all, what's its noble gas that you would use? Argon. So you would expect chromium to be argon 4s2 3d4. But in fact, the actual one, and that's because if I can half fill my d orbital, it's more stable. So in actuality, it's argon 4s1 3d5. Okay? Now both of those are half-filled orbitals, so it makes it more stable. Okay? Nature just likes to do crazy things. There's always an exception to the rule, right? Okay? So this was chromium. If I was going to do, say, silver, which is Ag, okay, I would expect what? Krypton, 5s2, 4d9. But what I actually have is krypton 5s1 4d10. Okay? So that one just does it a little bit differently. So then in the next line on what comes after silver is cadmium. Then cadmium would be 5s2 5s2 4d10. So then it would be the full shell. Okay, or the full sublevels of S and P, not a full shell. Okay, any questions on that? It's basically you just have to memorize it. Okay, on your chart like this, I don't know if you noticed it when I had it up the other day. I had these arrows right here, and no one asked me, why do you have those arrows right there? Huh? Why do I have those arrows there? I'm glad you asked that, Natan. Above this arrow, I would put S1 D5. So that you know that particular one fills differently. S1, D5, above chromium, molybdenum, tungsten. Okay? So I'd cross out the D4 and say this is what you actually get. And then on the, where it says D9, where you have copper, silver, and gold, above that I would write S1, D10, so that you kind of get used to that. Okay? And those are the only exceptions that I make you memorize, is those 5. If If you want to throw tungsten in there for the heck of it, you can because it's in the same group. Yes?
So the first one's S1, D5?
Yes. For chromium, molybdenum, and tungsten, yeah. And then the group that it's actually going to be group 11, which is copper, silver, and gold. That's going to be S1, D10. Okay? And those are your exceptions. Okay? And the main reason they do that is because they're more stable if they feel that way instead. And nature always likes things in its lowest form of potential energy and more stability. And so it will do that to minimize the potential energy and minimize the electron repulsions. Okay? So now let's talk about ions, forming charged ions, and what their electron configuration would look like. Okay? So charged ions. When elements lose or gain electrons, they will form ions. Okay? When they lose electrons, okay, they are taken from the valence electrons. So anytime I'm gaining and losing, they're coming from the valence electrons. So if I'm losing things that are negative, I become more positive, right? So they're called cations when they lose electrons. When they gain electrons, they're gaining things that are negative. So now they have more negatives than positives, so they are negative, okay? So they have cations and anions, okay? Cations are positive, anions are negative. Here's the way I've always taught kids to remember the difference. Are you ready? It's not are you ready? It's cations are positive. And there you have it. You will not forget now. You will not forget now. Okay? Okay? Well, there you go. So, how does that affect their electron configuration when they're gaining and losing electrons? Okay? So we're going to do one positive and one negative one. Okay? So the first one we're going to do is sodium. Okay? Sodium likes to lose one electron. So normally sodium would be 1s2, 2s2, 2p6, 3s1. Okay? So it loses an electron. When it loses an electron, it is Na+, because now it has more protons than electrons. Okay? So I literally take out that last electron, and then it becomes 1s2, 2s2, 2p6 is its electron configuration for the sodium ion. What do you notice about its electron configuration as an ion? What is it? It is stable, and it has the same electron configuration as what? Neon. It has the same one as neon. Okay? It does not become neon. Let's make that clear. Okay? Why does it not become neon? It still has the same number of protons. Very good. And remember, we always identify elements by its protons. This is why we identify by protons and not electrons, because protons are available to be lost, gained, or shared. Okay? And when we get to bonding, you'll see that they lose, gain, or share electrons in order to reach that stable octet. They're all trying to get to that octet, which is 8 electrons in the outermost S and P. Okay? 8 is great. That's what they're trying to get to. If you go on to take, and as we go further in the year, and especially if you go on to take AP Chem, we'll explain that in much more detailed and a lot more, well, I don't know how to say that, but we're doing it the easy way right here. 8 is great. That's what they're trying to get to. Okay? Now let's look at fluorine. Fluorine's configuration is 1s2, 2s2, 2p5. Okay? Fluorine likes to gain an electron. So now it has an F with the -1 charge. You can just do minus or you can do -1. Either way. Okay? -1 charge. So now we add an electron, so it is 1s2, 2s2, 2p6. So it now also has the same electron configuration as neon because it gained an electron, which is what they're trying to do. They're all trying to get to 8 in their outer shell. Okay? These are things that are called, I'm not going to ask you to remember this, but they're called isoelectronic because they have the same electron configuration as each other. So all these three things, sodium ion, fluorine ion, and neon would have an isoelectronic electron configuration. Just means they have the same electron configuration. Okay? And that is, I believe, where we end today.
Yay.